Okay, I'm making this recording for Laura because she was not able to come to my talk today, and also for Michael. So I was already introduced, and then I was up there, and so I didn't need to read this slide. But my talk is about the use of mobile apps to enhance student enjoyment and skills in recreational mathematics. This abstract I did not read. I always put an abstract on my slides for historical reasons so I know where I give the talk. And this slide, people in my session would have recognized this phrase because the individuals who are running the session listed this as one of the goals of the session, which is to answer many different kinds of questions, one of which is how can recreational mathematics be incorporated into regular classroom activities. American University is in Washington, D.C. Even though it sounds like a made-up name, it's a real place. The course that I take this discussion from is called Great Ideas in Mathematics. It appeals to a wide range of abilities. We have students in there, well, if they have a severe difficulty in algebra, they're not invited to come to this course. Also, if they are ready for calculus, they're not invited. But there's a wide range of abilities in the middle, and they're all invited. It's dependent mostly on whether or not the course is acceptable as their math requirement based on their major. So most of the majors we get are public policy or international relations. The STEM students and business students have their own math sequence, so they pretty much don't come in this class unless they're using it as an elective. The course aims to develop problem-solving skills and expression verbally of mathematical concepts. So they work on topics they've never heard of before, and they work on puzzles in groups, and the writing is what they would do on their exams or homework. The speaking is typically in groups. They could speak to the whole class, but mostly the speaking part is in their groups. Many different topics are covered. As I said, it's typically topics that they have not heard in high school. So American University gives us a wide breadth of a wide amount of freedom in choosing the topics. So for example, knot theory is something that is only taught by one of my colleagues who has done this extensively. I do Rubik's cubes and projective geometry, and that's kind of my thing. But a lot of these topics we can also find in textbooks. So for example, voting theory, probability, logic puzzles, things like that we will find in a textbook. But when we make up topics on our own, there are not materials for those topics, so we would make up our own materials to go with those units. And this is where my app came in. So I had created some classroom materials for the students, and they were working on them in groups, and I was circulating among the groups, telling them whether they'd done the activity correctly, and I wanted to automate this so that they could practice it outside the classroom. So I will show you the first puzzle, and I actually invited those in the audience, if they wished, if they would prefer to open up their devices and go to this URL, they were welcome to do so. I also told the audience that this typically will take 20 to 30 minutes in class, but because they're so bright, I expect them to figure this out very quickly. So I had the audience stare at these two panels and try to tell me that what the rule was. And I told them that one panel adheres to the rule entirely, and in the other panel the rule is broken. Can they figure out what the rule is and how it is being broken? And one individual fairly quickly raised her hand and indicated that this row contains 3 black squares, and that seems to be violating a rule. And I said, yes, that's correct. And then I prompted them, saying that also there's a rule for the columns, which is the same as the rule for the rows, so what's going on? And then somebody mentioned that the second last column has an odd number of black squares. So indeed, if you take this black square right here where my cursor is, and you flip it to being a white square, then what you end up with is every row and every column has an even number of black squares. This is what the app looks like that I gave my students. So what they're supposed to do is click on the incorrect square, and then it increments the counter telling them how many they have done correctly. I want to credit Tim Bell. He's from Australia, and his organization is called CS Unplugged, because what happens when you unplug a computer is you get math. Okay, so he has a whole bunch of activities, and he goes around to conferences talking about these activities you can do with kids of different ages to explain mathematics, but you call it computer science. So if error correction app or the error correction game, you're trying to teach kids that this is something you might use in computers in order to reduce errors in data transmission. So if you have a file in computer science, you may consider this portion, like everything except the last row and the last column is your data, but the last row and the last column is there just for error correction purposes. However, mathematically, we don't actually care which part is the error correction, because mathematically we only see if the rule is being violated. So in this case, we will find that the rule is broken in the second row and the first column, and so we find the incorrect bit, and we will click on this square that has an X. Okay, second puzzle I'm going to show you, I'm not going to actually show you how to do. I actually wrote many apps, but I selected 3 for this talk. I selected my favorite app, my student's favorite app, and my student's least favorite app. This was my student's least favorite app. So it's a UPC code quiz, and what I would do is I randomly generate a UPC code, and you could actually scan this with a barcode scanner, and I remove 1 digit, and I asked them to go off on a piece of paper, and they would spend 5 to 10 minutes, and they would calculate the correct answer, and they come back, and if they click, maybe they click a 2 and it would turn red, maybe they click a 4 and it would turn red, but then when they click the 8 it turns green to tell them, aha, you got the right answer. So this they did not like. The missing digit is 8. You can go ahead and Google that if you're actually curious, but it's not relevant for this discussion. That's an algorithm that anybody in the session would have no trouble working it out. Okay, the third puzzle. This one is about projective geometry, but let me first discuss with you the mechanics of what was happening in the classroom, and we'll later talk about the rules and the strategies. What I had given each student was a pile of 13 little markers, maybe 3 or 4 centimeters on a side, okay? And they were all over their desks. So they each had 13 of these little cards, and the cards each had 4 symbols on them. And what I asked them to do was to take and discard 4 of these cards. And the remaining 9 were to be placed in a 3x3 grid. And then I will walk around the classroom telling them whether they had a correct arrangement or an incorrect arrangement. So that's the high level. And but that was what was happening, and this is why I thought to write a computer program that could automatically tell them if their arrangement was correct. The original version of the app, simply all this instruction says is you can click on a card to grab it, and then you click on another card to drop. And so the grab and drop actually swaps 2 cards with each other. And that's all that says in the instructions. When the arrangement is correct, the screen turns green, and a picture pops up congratulating them on a correct arrangement. Even though my students very much loved this app, the problem with the original version was that only the students who actually knew what they were doing were able to practice and reassure themselves. The students who didn't quite understand how to do it had trouble getting through it. And so even though this to-do list is everything I already said in class over and over and over, I implemented the to-do list so they could watch their progress and reassure themselves that they were going in the right direction. So for example, if they made a mistake and they messed something up, one of the check boxes might uncheck, and they may not have realized that they had succeeded in a condition, but then later they did something to violate that condition. So this way they knew their progress was in the right direction. Now, again, I asked the audience, I said, because you guys are very smart, I'm going to ask you now to look at the solution and reverse engineer what the rules were that went into making this a correct arrangement. And somebody put her hand up and said, actually, I know how this works, so maybe I shouldn't answer. And I told her, well, just hold off, let's give somebody else a chance, but if no one answers, I'll come back to you. And then somebody recognized that each row of the 3x3 grid, each card has a common element. So for example, I've circled the common element for each row. And likewise, each column has a common element. But not only this, each diagonal and each counter diagonal. And if you notice in the diagonals, I didn't draw the third diagonal just to keep the diagram from getting too messy. But this is actually on a torus. That 3x3 grid is actually on a torus. So there are actually 3 diagonals in each direction. And something I did not put on the slides, but I mentioned, is that if you notice, the discarded pile all contains one common element, and it's not an accident that it looks a little bit like an infinity symbol. For those of you who have studied this before, you'll understand the joke. So there are 134,784 correct arrangements, so the students will not stumble upon it by accident. That's pretty much given. I've never heard of anyone doing it by accident. Okay, so given those 3 apps, again, there are many more apps, but for the purposes of this talk, I'm only talking about those 3. Which apps did the students like and which did they use? So I actually gave them a Likert scale survey, which asked them to rank each of the ones we used in class that semester as to whether or not they used it and whether or not they liked it. And not surprisingly, the exercises that they knew were going to become exam questions were heavily used. That's true. Okay, this was by far their favorite app. And this kind of surprised me because I thought they'd use it a couple times and get bored. But one of the things I did is on the Fibonacci numbers, I had the screen change color. And some students ran the counter up into the 20s and 30s, which I thought was crazy. I thought that once they understood, they would stop using the app, but that's not what happened. All my students mastered this concept, and by mastered, I will say they mastered it even if they didn't receive full credit on an exam question. So the question of whether or not they mastered the material was separate from the score they got on the exam question. It was a separate question. As I did not penalize for clerical errors when determining whether I believed the student had mastered the material. Yep, the students loved this, they liked it, and there was only ever one version of this app. Okay, the barcode question was the least popular app. It says of these 4, but it was actually pretty much the least used app of all of my apps. It was less popular than the other ones, and I only ever made one version. You can see that the mastery level is very low. Again, the mastery level doesn't mean, for example, 52% mastery doesn't mean that half the students got a 0. Most students got partial credit on this question. But to claim mastery, I felt that they had to demonstrate comprehension on each step of the exercise, even if the follow-through wasn't correct. Well, for projective geometry, it was really good. Again, there were 2 versions of this app, high levels of enjoyment and high levels of use. And the newer version unlocks the secret logbook and also gives the intermediate feedback on the process. The students very much enjoyed signing logbooks. For all the apps that I had logbooks for, they liked signing the logbook and proving to me that they reached the puzzle solution. They liked that. The mastery levels, you can see, jumped up when I changed to the new version of the app. And you see there is a small increase between exam 1 and the final exam. This is the same group of students. They knew in both cases that this question would be on the exam, but by the time the final exam rolled around, they put in the effort to make sure they understood that question, which, as you can see, it was not the case for this one. The same group of students, only a few more mastered this concept, but they were told this would be on the final, and they were also told that this one would be on the final. But many more students were able to achieve mastery of this subject. I found that my more effective apps, the ones they liked more, followed these guidelines that I found from this paper that says the code should be designed for short bursts of activity, and so on and so forth. And I feel that my code adheres to these principles with the exception of this requirement. Code should be designed for short bursts of activity. And this is my challenge and something I would like some feedback on, which is there are many concepts in mathematics which require more than a short burst of activity. So I'm torn between designing an app that will be something they enjoy and use, and the needs of what I feel the needs of the material are. And I'm having trouble balancing out those two opposing needs. Or to me, I feel like they're opposing. Also, I saw dramatic improvement in the mastery when the app was adjusted to provide incremental feedback. They really appreciated this. Even though it's exactly the same instructions I gave them in class, having that feedback that says, yes, you're going in the right direction, you're following the instructions correctly, keep going. They really appreciated that. They very much enjoyed signing the secret logbooks that just magically opened up when they solved the puzzle. And they appeared to not like having to work on paper and transfer answers back to the device. The conference, the session organizer said after my talk that he knows of some research that actually gives a different result, that in that study many students were in the study, and that they actually enjoyed working problems on paper and then getting feedback from the computer. So that's something I need to pursue and read up on those papers to see how it's different from what I'm doing in my barcode app, to see if I can improve student enjoyment on that. Future work is I plan to keep writing apps and adjusting them to see how the modifications help, and giving students surveys about what they liked or didn't like. And my big question is what to do about higher level math courses, because again, I'm concerned that short bursts of activity are insufficient for mastering the higher level concepts. Is it even appropriate to try to design that kind of app for the higher level concepts? My future direction that I'm moving in right now is I have a couple colleagues and we're thinking in terms of writing some online games. So the game of hex, but instead of on a square or a hexagon, to do it on a topologically interesting surface. So that's a direction we're planning on going. I will be looking forward to working with people as opposed to just writing apps by myself. Okay, and at this point I ended my talk and sat down, and the way my session was organized, all the talks were given first, and then the discussion continued after that for about 45 minutes, but the discussion typically was more general, although a few times people shot specific questions to specific speakers. Okay, so I hope that helps you understand what my talk was about.